Let me just remind us of some things here from the calendar. Hopefully, you guys all were able to turn in your assignments yesterday through Teams. But those of you who are late, you can still turn it in, but you'll just email it to me or send me the remind. You'll still get the majority of the credit. You can still get 90% on your assignment. But this is going to count as a quiz grade, so you definitely want to, if you haven't turned it in, you definitely want to turn it in. Otherwise, it will hurt your grade. So, so today I want us to go through integration methods, part B. So this is topic 5B. The FRQs that we finished worksheet, we finished number 3 yesterday, right? We identified that the importance of applying extreme value theorem. After we find our critical point at the end, we tested our critical point along with our endpoints with our original y of t function, which will tell us the exact amount of sand at those moments in time, and whatever is the lowest of these 3 values must be the absolute minimum. So we found that to be true, kind of applying extreme value theorem within this larger context antiderivative word problem. So we did 1 and 3. Your homework is going to be the rest. So 2, 4, 5, and 6. Okay, so I did not put that link on the website because it's the same as this worksheet that we worked on yesterday. Number 5, I think, is a really good problem that I wish I had time to go over. So maybe I'll spend some time on Friday going over. Friday is asynchronous day, but maybe I'll spend some time just over the course of the day and record it. Actually, I do have a recording of number 5, but maybe I'll have another recording where I'm going it from the beginning. So I can kind of spell out each of the steps. So I still haven't figured out what I want to do for Friday. Again, nothing's required on Friday. I'm not going to give any new assignments on Friday. Just really, hopefully, it's a catch-up day to allow for you to either catch up or work on things you need to work on. But Friday, I am going to have a help session in the morning and afternoon for those who are wanting to get some additional support for the Chapter 7 test. If you want to do a recovery on that Chapter 7 test, I know some of you are still waiting for me to return your test, so hope I'll do that during lunch today. Or if you haven't received the test details from me, you can send me a remind and I can send you your test so that you can do corrections on that. The assignment, the assignment for Chapter 7 recovery is on Teams. I put that on Teams yesterday, so that's going to be due on Sunday. And you need to let me know by Friday whether you want to be taking that recovery test or if you're interested in wanting to take that recovery test for Chapter 7. Okay. So we're going to go through the integration worksheet today. Tomorrow it will be we'll start our review for our quiz, our FRQ quiz. I'm calling it quiz number 2 because quiz number 1 is just all the homework assignments that you guys are going to turn in, and so that's what you just picked up today. So you guys picked up, if you're in class, you picked up the worksheet and the homework, but then also tomorrow's worksheet, since tomorrow is going to be virtual. So I still haven't put up the homework for tomorrow's date, so I'll have that link ready later on today. But we're going to be working towards our quiz. Our quiz will be next Thursday, so we'll have tomorrow to start that process of reviewing. We'll have Monday to review, we'll have Wednesday to review, and Thursday's your quiz. Okay. Any questions about the calendar? Okay, all right, so let's jump into our worksheet for today. Okay, so we're going to start off with, I initially wanted to just do a worksheet just going over the basic integral rules like power rule and then U-substitution and like long division, synthetic division. But I think maybe it's better, and hopefully that's still relatively fresh in your mind. I want to just hit the antiderivative topics in terms of the ones that are, or at least the format of what AP exams could give for these rules and formulas that are kind of spread out across chapter 4. So kind of gives us a chance to kind of see the variations of problems that can be presented on an AP exam. So let's start off with Riemann sums. Okay, we started with Riemann sums at the very beginning of chapter 4, where we're not so concerned about the accuracy of our approximation. We're more concerned about the method, right? So being able to apply the appropriate approximation method to find the area of a region, to approximate the area of a region. So with Riemann sums, we did left-handed rectangles. We practiced using middle rectangles. We practiced approximating using right-handed rectangles, and then also trapezoid approximation. Okay. So let's look at number 1. The function f is continuous on the closed interval from 1 to 10 and has values shown in the table given. Using a right Riemann sum with 4 subintervals, what is the approximation of our definite integral from 1 to 10? So we'll be using right Riemann sums, rectangles, right-handed rectangles. And so we're going to be essentially applying over the course of these 4 subintervals, adding up areas, adding areas of these rectangles, which is just width times height. So there's a very specific way that we arrive at these widths. We're going to be drawing these brackets that sit above these ordered pairs. But the way that I want us to draw these brackets is I want us to, once we identify the subinterval, you're going to start and end in the middle of the ordered pair. Okay, so let me show you what I mean by that. So my first subinterval is between 1 and 3. So I'm going to start in the middle of the ordered pair and end at the middle of my second order pair. Okay. And then my bracket, my second bracket, I'm going to pick up where I left off, center of my box, and move to the center of my next box. Okay, if you draw it a different way, if you draw it from end to end, where the lines are, then you're not going to be able to truly see what the subinterval is. You won't know what to subtract. So I think going from center to center is going to be the best way. And then make sure you don't skip an order pair, right? Whatever you ended with, you're going to pick up where you left off. There's always going to be an overlap with each of these brackets. Now, you're going to be picking off the width from these brackets. That's where the width component of my rectangles will come from. We're going to take these x values, we're going to subtract it. We're going to find the distance between each of these x values. So distance from 1 to 3 is the same thing as 3 minus 1, which is 2. The distance from 3 to 5 is 5 minus 3, which is also 2. Distance from 5 to 8 is the same thing as 8 minus 5, which is 3. And then 10 minus 8 is 2. Okay, any questions there? Now the way you pick off the height is from the second row, from f of x. But we're not going to be subtracting anything there. We're just going to pick off whatever number is suitable based off of the description of rectangles that we want. So let's look at, see if we can find the areas of these rectangles now. So we'll say the definite integral from 1 to 10 of f of x dx let's find the area of my first rectangle. That's going to be the width of my first rectangle, which is 2, width times height. Now the height is going to have to come from the second row here. So which one do I choose? Do I choose 7 or 12?
12.
Yeah, because I'm doing right-handed rectangles. So my first subinterval, the 7 would be for left-handed rectangle, but the 12 is on the right side, so that's me for the right-handed rectangle. So 2 times 12, width times height. There we have the area of my first rectangle. Okay, moving on. Our second number that we see, that's going to be the width of my second rectangle. And then what's going to be the height of my second rectangle?
16.
Yeah, 16, right? If I look at my second and third order pair, the one on the right is 16, so I'm just going to pick that value out. Third subinterval, width is 3, and height is going to be 23. Last subinterval, width of 2, height of 17. We total them together. 159. Okay, any questions with that? Okay. Okay, now we're moving on to exact area, exact region. But we're able to do that for number 2 because we have some nice geometric shapes. Okay, so we're going to be finding exact area, but because these have fallen in nice geometric shapes, we're just still going to rely on our geometric formulas to find our, or to involve these integrals, these definite integrals. So definite integrals involving graphs with geometric shapes. It says the graph of f of x contains 4 line segments and a semicircle as shown. Evaluate each definite integral by using the geometric formulas. So I think one thing that I see students make mistakes with is identifying the shaded region. I think sometimes we are drawing or we're identifying shaded region that's not part of the diagram. And I think something that will help is recognizing that we're only concerned about the region between the x-axis and the graph. Okay, so let me highlight where the region that we're concerned about. So in orange, I'm going to highlight the x-axis. And then in another color, I'll highlight the graph. So the region that we care about is only what sits between my highlighted lines. So I don't look at anything here because this doesn't sit anywhere between my 2 lines, right? But I'm going to look at the region here because that's between, that's between, that's between, and these are between as well. So I'm going to just shade in lightly so I can see these geometric shapes kind of, or these geometric figures kind of take shape. So what I see in front of me is I see a triangle, a semicircle, a small triangle, and then a rectangle. We're going to be totaling the areas of those regions, but we have to keep in mind that we're doing definite integrals, which is area related, but we're not pushing it into a top minus bottom formula. So what that means is any region that's below the x-axis is going to have to stay negative. So we'll find the area of triangle here, but we have to assign that to be a negative. This triangle is also below the x-axis, that's also negative. The rectangle is below the x-axis, that's also negative. But the triangle above and the semicircle, these are positive. Okay. So we're asked to find the definite integral from -5 to 5. So we're going from one end to the other. And we're going to total those regions up. So my first figure from left, this is a triangle. My formula is 1/2 base times height, but it's below the x-axis, so I'm going to assign a negative in front. -1/2. Oops, let me put this a little bit higher. base times height. My base is 1 and my height is 2. My triangle, next, my second triangle here, 1/2 base times height, but it's above the x-axis. I can let it remain a positive value. We have a semicircle, 1/2 pi r squared. What's the radius of my semicircle? 2, yep. From the radius of the center to a point on the circle here, 2 units. Triangle below the x-axis, that's 1/2 base times height, but I need to make sure I have a negative there. And finally, my rectangle here, width times height. Combine those values together here, I get -1 plus 2 plus 2 pi minus 1/2 minus 2. Clean this up here, the 2's cancel out. -1 minus 1/2 is -3/2. Or if it's a multiple choice question, it may be presented as one fraction with a common denominator. Okay, so either is fine. All right, questions with number 2? Okay, moving on to number 3. This is finding the depth integral of absolute value functions. This is something that I skipped over early in the year in chapter 4. I just had to, because of time constraints, I didn't get to it, but I knew that I was going to come back around and pick it up when we did review. So this is a problem. If it were to show up on the AP exam, it could show up on the non-calculator section, right? It would never show up on the calculator section because it would be too easy to just plug in and find. So if you're taking the May exam, there is going to be a non-calculator section. So I want to make sure that I go over a problem like this. The nice thing about this problem is that it looks messy because we're not used to absolute value functions, but because of the shape of it, we're going to be able to rely on geometric shapes that we recognize. Okay, so whenever we see a problem like this and we're asked to find the depth integral, the easiest way is let's just draw the graph. We're going to be able to create 2 triangles, and we're going to just add the 2 triangles together. Okay, so let me do a little bit of a reminder here. What do you guys know about the shape of absolute value of x? What does that look like? Anybody remember what that shape? Yeah, V, right? V shape. Either V right side up or V upside down. So here, absolute value of x is just a V with a vertex right at 0, right? So just a reminder. And because of those straight diagonal lines, it's going to lend itself to a nice geometric shape that we can use. So let's focus on what the absolute value of x minus 2 looks like, and then we can worry about the bounds. So the absolute value of x minus 2 is also going to look like a V-shaped graph, but that vertex is going to be shifted. Okay, and the way we find that vertex, which we associate as the center of our graph, is we're going to set the inside portion equal to 0. So if I set x minus 2 equal to 0, I get x equals 2. This is going to be the center of my graph. Okay, so we're going to sketch out our graph. It's basically just going to take that vertex and shift it over to an x value of 2. We know the graph is right side up because there's no negative sign outside the absolute value. So I'm going to start from 2. I'm going to just extend the graph into a V shape. The question is, how far do we extend it? And we're going to extend it as far as our bounds take us. So we're going to extend as far left as -3, and we'll extend as far right as +5. Now, if you look, what sits between the graph and the x-axis, we can kind of see these triangles take shape, right? So let's see if we can just shade in that so we can kind of see these shapes a little better here. So essentially, we're just going to be adding these two triangles together, and that's going to represent the depth integral of our problem. Okay. So the next thing we need to do is we need to identify the heights. We need to find these endpoints, because these endpoints, the y values at these endpoints will help us represent the heights of these triangles. So I'm going to find order pairs at these points. I'm going to plug -5 into my function. So -3 minus 2 is -5. What's the absolute value of -5? Just 5. Okay, so I'm going to just notate that as my y value. I'm going to come back to it, just still in the information gathering stage. Okay. Now over to the other side, I'm going to put 5 into the function. 5 in for x. 5 minus 2 is 3. So there's my order pair, 5, 3. Okay, so we're ready to find our area here. We know the depth integral from -3 to 5 of the absolute value of x minus 2 is going to be equal to the areas of these triangles that we see in front of us. So area formula is 1/2 base times height. And we're just going to find the areas of these two triangles. Let's start with the one on the left. 1/2 base times height. What's the base length of my triangle here? 5. And then the height is also 5. Okay, we're focusing on that y value, right? That y value is going to tell us how high that point is. Okay, 1/2 base times height. That's the area of my first triangle. Second triangle, 1/2 base times height as well. What's the base length of my second triangle? 3. And the height is also 3. Total those together, we get 25/2 plus 9/2, which is 34/2, which is 17. There we go. Not a difficult problem, but it is very unique, right? We don't do integral problems usually like this. So I put another one of these problems on the homework sheet so that you guys can get practice, but I think after you do 1 or 2 of these, it's easy, right? Just if you can draw the graph, if you know that you're targeting 2 triangles, just have to find those endpoints and then do the, remember the formula for triangle, 1/2 base times height. And you're always adding 2 triangles together. Okay, any questions?
Yeah, can you go over how you got the height again?
Sure. Okay, so the way I got the height is I took -3 and I plugged it into the function. And my function is absolute value of x minus 2. So if I plug -3 into the function, I can find that y value, right? So what's -3 minus 2?
Okay, thank you.
-5, right? And then the absolute value of -5 is going to be a +5. So
Right.
yeah, just take your endpoints, enter it into the function, whatever you get back in return, it's going to represent the heights of your triangles. Okay. Any other questions? Are we good? All right, number 4. This is a review over another concept called the second fundamental theorem of calculus. And this theorem is highlighting the fact that if I am doing the integral and a derivative on top of the same function, my function is not going to change much, right? Because I am doing a process, but then I'm undoing it. But along that path, that upper bound is going to do something to the expression that's going to have some lasting effect. So even though the function is not going to change its structure, that upper bound variable is going to have an impact as we go through those processes. We're not going to go through the full process. We're just going to jump to the end. So it's kind of basically like a shortcut. We're not going to go through the whole idea of taking the integral, depth integral, evaluate the bounds, and then taking the derivative. It's just, there's no need to do that when we already know what the end result is going to be. So here's what is going to happen after the dust settles through those two processes on the same function. What's going to happen is that upper bound is going to end up getting lodged into the function. And then what's going to happen as well is that upper bound from the derivative process is going to end up showing up as a derivative being multiplied to the expression. So let's look at this problem here. It says if f of x equals the integral from 0 to root x of cosine of t squared dt, then find f prime of 4. Before we can find f prime of 4, we're going to find f prime of x. So let's find the derivative first. I want to find the derivative of this expression, but rather than taking the derivative, I'm just going to represent that I do want to take the derivative. So I just want to say I want to take the derivative of this expression. So I'll write it as d over dx of my problem. And also I wrote it this way so that we can match it up perfectly with the rule that I want to apply right above it. So not a whole lot's going to be done to the cosine because I'm undoing the processes of each other. But that upper bound is going to have an impact. So can you tell me how can I represent f of p of x? What does that mean?
Like y value that the p of x function produces, put that in for the x value of the x function.
There we go. Yep. So we just take that upper bound and we insert it into the variable of our expression. So I'm going to just take that root x, insert it into t because that's what the rule says. Times my upper bound's derivative. So how do I take the derivative of root x? Okay, well, first up, how can we rewrite x square root of x?
X to the 1.
Yeah.
Oh, x to the negative 1/2.
Yeah, so we go through power rule, right? We bring the 1/2 down first.
Yeah, that's picking cube.
Right. Oh, okay. Oh, cube root, I see. So then we subtract 1 from the exponent. 1/2 minus 1 is negative 1/2. So we're able to skip a lot of things, right? We're able to skip derivative and integrals and just jump to the end. So we consider this as a shortcut process. Rather than going through the whole process of derivative integrals, we're just going to jump to the end because we know that these two operations will undo each other. Now, we can do a little bit of cleanup from f prime, and then we can worry about that 4 getting evaluated. So here's my cleaned up version of f prime. The root x squared cleans up. I'm going to push that x down to the denominator, share the same space as that 2, and I'm just going to rewrite it as root x, just make it easier to evaluate for our next step. But we're just cleaning up. Next step, I'm ready for my f prime of 4, so now I can enter in 4. So cosine of 4 times 1 over 2 root 4. All right, do a little bit of cleanup here. Root 4 is 2. 2 times 2 is 4. 4 is going to remain in the denominator. Cosine of 4 over 4 matches my answer choice B. Okay, any questions with second theorem? We're going to see it in the context of some FRQs, so maybe I'll bring that up. Oh, actually, it's going to show up in your homework, so I try to explain it in words, what's going on there, but maybe I can create a video on Friday going over the homework during that asynchronous day. Yes?
What is the cleanup process to get to?
Oh, from here to here? Okay, so what I did was I squared the square root, and so I was able to get the square root and the square to cancel out. So this left me with cosine of x. And then this x to the negative 1/2, I pushed it down to the denominator, which will be 1 over 2 x to the 1/2, and I just made it square root of x. And then once I'm here, it makes it easier for me to plug in the 4. Did that answer your question? Okay. All right, let's go to the back. There's a couple of things that I think is good for us to go over, like average value theorem, evaluating or looking at the first theorem of calculus and how we can do these variations that show up quite a bit on the AP exam. But I just want to end with this, with U-substitution. These are U-substitution variations that we typically did not do during our Chapter 4 unit because we're just doing kind of straightforward U-substitution problems. But AP exams like to do this where they mix an expression into a function notation and then expect students to be able to go through U-substitution in that form. So I just want you guys to be accustomed with that form. Since these show up quite a bit. I feel like I see at least 1 or 2 variations of these across multiple choice or free response. So I just want us to do number 7B, just to kind of get our feet wet, and then we can you guys can get practice with these types of U-substitution in when it's provided, when the problem is provided in this form. So number 7B. It says if our function is continuous and the definite integral from 1 to 8 of f of x dx equals 15, find the value of the definite integral from 1 to 2 of x squared f of x cubed. Now we're looking at this and we're saying this is kind of strange, right? We usually don't do definite integrals when there's a mix of expression and function notation. But we are given this information. So the hope and the idea is that maybe I can get a way to make this look like this expression so I can actually somehow use that 15 in my answer somehow, right? If they give this to us, it should be connected somehow. But right now, it looks like it's tough to see what that relationship is. So the whole purpose is U-substitution allows us to take a messy expression and clean it up into something that's more manageable for us to work with, right? So we're going to apply U-substitution with this messy expression in the hopes that we can get this to look like this somehow, some form, so that we can see how the 15 plays a role in allowing us to make substitutions or create a value out of it. Okay. So we're going to apply U-substitution here. Okay. We want it to clean up. We want it to be an easier form to match with. Okay. I just rewrote the problem here. Now with U-substitution, when we did U-substitution at the beginning, I always said, all right, how do we find a U value? Usually the U value for the easier problems, I just said, find the parentheses, right? Usually if you can find the parentheses, that's where your U value is located. As we got into more complex problems, that wasn't always the case, but that was how we kind of got the ball rolling in terms of, right, let's start with some easier problems here. Same thing here. This form looks different, but we're going to find U value the same way that we did at the beginning when we were introduced to U-substitution. We're going to seek out that parentheses, and that's going to be where our U value is most likely going to be located. So I'm going to underline this. Remember how with U-substitution, we always focused on the parentheses, and then we immediately also focused our attention on dx, because piece by piece, we want to convert our expression to be in terms of U. So we'll let U equals x cubed. Our derivative, du dx, 3x squared. Cross multiply to solve for dx. So I'll say 3x squared dx equals du. Divide both sides by 3x squared. And now we're going to substitute what we found into the expression in the hopes that we can eventually get our entire expression in terms of U. So I'm not going to carry the bounds over, but I'll carry the x squared over. We'll talk about the bounds later. Replace the x cubed with U. Replace the dx with du over 3x squared. Okay, what do you guys see here?
They cancel out the x.
Good. X squared goes away. That's good. And what do we have to keep track of, though? Yeah, the 3 pushes out as 1/3, right? So we always did this with U-substitution. If it worked, all the x's goes away, but there may be some leftover coefficients that we don't want to forget about, so I like to push those out in front. Okay, so far, familiar, right? But it's just a different form that we're not used to. It's cleaned up. I know it's a different variable, but essentially we can match this and say that we're closer to where we were than what we started with. Okay. But here's something else that we have to take into account is that these bounds, we want these bounds to be represented as something in terms of U so that we can get a clean match. Okay. Right now, the 1 and 2 are not compatible. Why is that? Different variable, right? The 1 and 2 is in terms of x, but we started that conversion process of our entire expression in terms of U. So we have to convert those x value in terms of U. We'll have to convert the bounds. Okay, so we'll convert the bounds. And the way we convert the bounds is I'm going to take my old x, my old lower bound, and I'm going to convert it to be in terms of U. And the way we can convert it is we look at the assigned expression that we created at the beginning. We said u equals x cubed. So if I can insert 1 in for x, I can find my updated u value, right? There's my conversion rate. So u equals x cubed. So u equals 1 cubed, which is u equals 1. So in this case, looks like after I went through the conversion, it still ended up being the same value. Okay. My old upper bound was 2. Let's see what happens there. My old upper bound was 2. I pushed it through this conversion. 2 in for x, 2 cubed is 8. My new upper bound is 8. So now I'm going to rewrite my expression here. 1/3 definite integral from 1 to 8 f of u du. Now, do you see something that we can pair with? Do you see that match occurring for us here? F of u, I know it's a different variable, but essentially, if I replace u in terms of x, I'm able to get that match to occur. So, what do you think I can replace this portion with?
15.
There we go. And if I replace that with 15, I'm keeping track of that 1/3 in front. So what's 1/3 times 15?
5.
Yeah, 15 divided by 3 is 5. So this is how we need to be able to use U-substitution for certain problems that is in function notation form. Similar process with 7a, similar process with 7c. I also included a couple of problems on the homework, but maybe we can finish the rest of this page tomorrow, and then we can begin the quiz review as well. Okay. All right, any questions with this? All right, thanks everyone. Hope you guys have a great day. I'll see you guys on Teams tomorrow. Okay, have a great day, guys.